Okay, welcome all participants. This is the first international webinar organized by CEPET, that is the Risk and Disaster Management Coordinated Group from the Santa Catarina State University. And it composed the third Santa Catarina State Seminar on Education in Disaster Risk Reduction. The first edition of the seminar was held in Joinville before COVID pandemic, and the second edition was last year in Chapecó City, and this year will take place in the end of November in the city of Lages. We will be running a series of webinars, short courses, and roundtables. And this webinar will address then these insights of best practice for disaster management. This event will be shared by Dr. Virginia Grace Barros. She is Associate Professor at the Santa Catarina State University. And also Lakshmi Thapa, she is a PhD student and also representing the student consortium of ISPRS. And I will be adding both here, Virginia and also Lakshmi. And they will be then conducting this webinar and also presenting our distinguished lecture. So welcome both of you, and please start the session. It's open now.
Okay, Veraldo, thank you very much. Before all, we want to thank you, our lecturer, Professor Josep Maspla, for attending our invitation, and we would like to thank the event supporters for making this moment possible. I will briefly introduce Pep. Currently, he is full professor at the Environmental Science Department in the University of Girona and senior research professor at Catalan Institute for Water Research. As academic formation, he is graduated in geology and holds a doctorate in geology and a PhD in hydrology and water resources in the United States of America. His research interests are regional hydrogeology, dynamics based on field work, hydrochemical and isotopic data, and groundwater flow and transport modeling as well to determine water resource sustainability under human pressures. I'm sure we are going to have an excellent lecture about how groundwater's understanding and preservation can support decision making before and during extreme events, and also how to manage this strategic natural resource. Thank you very much, Pep, and you can go to the stage.
Okay, hello to everybody. I guess I can start the lecture now. First of all, I would like to thank the Santa Catarina State University for inviting me to this seminar, all of the people who has prepared this talk, and Virginia especially for inviting me, who's the one who contacted me. And just let you know that with Virginia, we know each other for almost 20 years. So here we are very formal, but we have a lot of confidence, and I really thank you, Virginia, because it's a pleasure to contribute to all this initiative you do from Joinville, or either Joinville or in Santa Catarina State. Anyway, it doesn't matter where are you now sitting. Okay, thank you to everybody for coming to this lecture. I'm going to put the full screen now and start the talk that is expected to last for, let's say, 35, 40 minutes. I don't think it will take more than that, because if not, you may all go to Netflix or something like that. The organization suggested me the title Understanding Groundwater's Impact on the Environment within this macro course on disaster risk reduction. So what kind of risk can we have? What does groundwater is associated to risk? It's associated to risk because water scarcity and groundwater scarcity can put at stake not only the human water supply, if that supply comes from subsurface resources, but also can have a larger impact on ecosystems. So the idea of today's talk is to get into the groundwater and explain its dynamics and its relevance in the way groundwater supplies water for urban demand, but also importantly is the environmental role of groundwater to preserve ecosystems. So today's talk will be in a very, let's say, basic level. So everybody will get into the groundwater topic very easily and understand that what happens in the subsurface is not unknown, but it can be known with quite a bit of detail if we took the appropriate measurements of groundwater levels, groundwater hydrochemistry, pollution. We can model, so we can practically get a lot of information and propose some managing actions that will preserve the resource and guarantee its occurrence, not only, I insist, not only for human supply, but also for environmental needs. Okay, in this first slide, I took a figure from the book that's portrayed on the right-hand side of the screen. There's a book called Groundwater in Our Water Cycle. It's free access, and it has been published by the Groundwater Project. I mean, it's a very simple book. It's about 100 pages, for instance, and it deals with every aspect of hydrogeology, of groundwater science. And for those who you are interested, I will say that one of the best things we can say of this book is that it has no equations at all. It's only concepts and concepts and concepts explained in a very easy way. I took one of the figures of this book, the one you have here in the screen, to show that below the surface, where you have all the trees, I mean, the geological formations that constitute, the underground, has porosity. Most of them have porosity. And if this porosity is interconnected, this geological formation also has permeability. So a geological formation that has porosity and permeability, it's called an aquifer. So the aquifer is not the water in the subsurface. The aquifer is the geological formation that contains water. Of course, water infiltrates from rainfall. I don't know if you can see the pointer here. Infiltrates from rainfall. It sustains vegetation and habitats in the surface, and it accumulates in the subsurface. So there is a moment, and there is a point that's called the water table, below which all the voids within the geological formation are full of water. This is what we call the saturated zone. And this is the water we can pump out to supply water for our needs. Above the water table, there is a small part of the geological formation that is not saturated with water. porosity is filled either by water and by air. And therefore, it holds a volume of water that we cannot extract to supply our needs. Indeed, the water table is an oscillating level. If it rains a lot, the water table will rise. If it doesn't rain, the water table will lower. The question is why it will lower? Because water is not static. There is a groundwater flux from the areas where water table is higher to the areas where the water table is lower. In this case, the groundwater flux goes from left to right. And another interesting thing of this plot is that the water table is connected to the surface water level of this lake, river, whatever is drawn here. Meaning that from a conceptual point of view and from a practical point of view as well, groundwater and surface water is the same thing. Both are a single resource. And we will deal with this aspect during this talk, during this lecture. So groundwater is fundamental for both, as you can imagine, not only for human supply, but because of this connection between surface water, it will be important for the preservation of stream flow and wetlands as well. So groundwater has this positive impact on aquatic ecosystems, and when there is no rain, it's groundwater who feeds the streams. So when there is no rain, all the water that flows through a river is indeed groundwater that has been produced by the aquifer, by the groundwater flow that we saw in the previous slide. It is also a main source for human uses, okay? Especially in dry areas where we do not have an excess of surface water, but the aquifers can be used to supply the water that people need. Later on, we'll see that if we exploit aquifers, if we take water from aquifers and there is no recharge, what we are doing is water mining, and this is quite dangerous because when you do mining, that means that the resources are not renewable. But at the beginning, we will think of groundwater as a renewable resource, meaning that there is some kind of recharge, mostly from rainfall, that will recharge, I didn't want to say the same word again, that will recharge the water we are taking from our uses. However, groundwater can be overexploited and polluted. And we don't want either of these things to happen. If it's overexploited, that means that we are taking more resources than the ones that they are renewed every month or every year. And if groundwater is polluted, that means it has no quality to be used, for example, for drinking, for cooking, for domestic use at the end. And these are the risks we want to avoid, because both overexploitation and pollution means a risk, because it means a loss of a benefit, and this benefit is called groundwater. And this risk happens not naturally. It happens because of a lack of management, by an abusive withdrawal or a bad use of our our garbage, that finally it gets into groundwater and modifies its hydrochemistry and includes pollutants in the groundwater cycle. So the point is that if we understand the groundwater systems and how they work. If we take measurements, we go to the field and we monitor wells, both the water table and the groundwater quality, we can have enough data for an accurate management that at the end will avoid the risk we're talking about, this risk of overexploitation and pollution. This is a very easy slide. I mean, everybody knows about the hydrological cycle. That means that water from the ocean just evaporates, it gets to the clouds, then one over the inland, over the continents, and there is rainfall, there is precipitation, and this precipitation may just evaporate or evapotranspirate, meaning that the biosphere, mainly the forest, will take all this water and bring it back to the atmosphere. This is called the green water, meaning that it's the fraction of precipitation that fits the biosphere, that returns to the atmosphere. And we, as humans, we cannot use this water to supply our needs. Also, this water that's consumed by evapotranspiration neither goes as runoff or stream flow, neither infiltrates to the soil to recharge the groundwater reserves. So understanding the hydrological cycle is really important, because at the end, what we can do is to make some calculations. We can express the hydrological cycle as a mass balance. And as a mass balance, we'll have some inputs. These inputs will be over a hydrological basin, over a catchment. Imagine that this picture is a catchment. We have a rainfall coming in, but we also have, or may have, some groundwater flux also coming into our area of interest, coming into the watershed, where we are going to take the water resources, whether surface water, whether groundwater, to supply our needs. In contrast, opposite to the inputs, we have the outputs, and the outputs will be the stream flow, the runoff that will flow out of the catchment. We have evapotranspiration, the green water we were talking before, and we also may have a groundwater flux that leaves the basin in the subsurface. If we put this into an equation, in the left-hand side, we have the inputs. Within the parentheses, we have the outputs, and the difference between them will be a change of the resources stored in the aquifer. If inputs are larger than the outputs, resources will increase, and that will produce an increase of the water table, meaning that the aquifer holds more water than before. Otherwise, if outputs are larger than inputs, the balance will be negative and the water table will decline, meaning that its contribution to surface water will diminish, and also the groundwater flux out from the basin will also change. So if we have no rain, we have a problem that our resources decrease, and also the environmental effect of groundwater by feeding the streams will also be put at danger. I already talked about aquifers, but let's go through a serious definition. I mean, the aquifer, I insist, is not the water. It's the geological unit or geological formation that contains, that stores the water, that lets the water flow because it's permeable. And it's also important, it allows withdrawing the water in an economical, physical way to supply our needs. And we also want this water to be of acceptable quality. Here we can talk about what will be a sustainable use of these water resources, But I think we can leave this concept for the discussion part of this evening, of this morning, for people in Brazil. Not all the geological formations are aquifers. If they are of very low permeability, we'll call them aquithards, meaning that they may hold water, but we cannot pump water from them. So we cannot withdraw water to supply our needs. But they contain water. Aquicludes are also geological formations that has a very, very low permeability or a very, very low porosity, meaning that they are not interesting for us as a water supply geological units. But they are interested from a hydrogeological point of view in the sense that they will confine the aquifers, and therefore that will permit having confined or unconfined aquifers, which differ mainly in the amount of water they can store and in the way in which their exploitation will be sustainable or not. The properties of a geological unit to be defined as an aquifer, as I said, are porosity, are permeability, but also the geological structure. I mean, we are talking about geological units. So we should not imagine aquifers as a box, as a cylinder. I don't know. We have to imagine aquifers are geological formations. This is a very well-known scheme about hydrological system. On the top, we have an unconfined or water table aquifer, if you see my pointer, and it is this geological formation that's on top of this stratigraphic sequence. When it rains over the fields, water infiltrates in this aquifer, and because there is a hydraulic gradient, it flows from the mountain areas down to the ocean. However, if we go deeper, we have this gray geological unit, which here it says somewhere it's a confining layer. This is a geological formation with a very low porosity and a very low permeability, meaning that water cannot flow through it. I will not like saying it's impervious, because only a very few geological materials are completely impervious to the groundwater flow. I prefer to saying it's a very low permeability, okay? In order to be rigorously rigorous with these concepts. What does it mean? It means that the confined aquifer, the thicker geological unit we have here in this scheme, this confined aquifer, because it is confined in its upper boundary, only gets the recharge from the mountain area when it reaches recharge area for the confined aquifer, meaning that all the rainfall falling down in the summit of the mountains will just infiltrate and recharge this confined aquifer, which will create a groundwater flow that will go again downward to the ocean. In its bottom part, we also have another confining layer that makes that this groundwater flow is limited within the boundaries of this aquifer. What is the difference between a water table aquifer and a confined aquifer? The difference is that water in the confined aquifer is at pressure. In the scheme below, what it represents is an analogy of the confined aquifer. We have the recharge area here in the mountains is represented by this part here. And the aquifer is this pipe that is here open in a lower elevation, which represents the ocean. So within the pipe, there is a pressure surface, meaning that if we had some small pipes, vertical pipes, and one of them is broken, water will flow out from him. And this is what we have here. We have this pressure line as a discontinuous line in the draw, we have a well here that is only open in the confined unit, and because the Earth's surface is below the pressure surface, we have what is called a flowing artesian well. This is just an example of the many aquifers we may have. What is the interesting thing here? The interesting thing is that if this is the recharge area, and here we have some human activities that may create some type of pollution, pollution here will infiltrate and change the quality of all the water resources stored in the confined aquifer. Okay? And water from these two wells will get polluted because of the human actions having part on the hills, on the top of the hills of this scheme. So, in order to prevent the risk of pollution, we should know what is the geological structure that defines the occurrence of the aquifers, and what is the extent of the groundwater flow, if it goes in this direction or in any other direction. This is a very simple scheme, so this is just 1D direction. We cannot make any other explanations on that. But groundwater flow, as you can imagine, is a three-dimensional vector. Therefore, we should take a lot of measurements to define, that will help us to define where the water flows to. But this is the scheme. How do aquifers look like? For instance, there is a cross-section of a fluvial area close to the ocean, okay? We had a valley. The valley was filled by about 60 meters of alluvium, of gravels, sand, clay, and silt, the typical sediments that you get in a fluvial or delta environment. And what we see is that the gravels here that form the gravels and the sand that forms the lower aquifer unit of this hydrological system is a finite unit. I mean, it has a boundary, and what is below this boundary, it's an impervious rock. It's not drawn here, but it's a marl. A marl, it's a kind of limestone with silt and has a very, very low permeability. So the aquifer is limited to this extension. And only holds the water that fills this porosity. So for us, it will be very easy to calculate how much water is in this lower unit. How? If we know the volume and we know the porosity, then we know the amount of water that's stored in this bottom aquifer. Then our task is, first of all, know the geology, know the porosity, estimate the resources, and contrast this volume of resources with our demand. If our demand is larger, then we will overexploit the aquifer. In this sense, we should take into account the stored resources, the recharge, and our demand. However, going back to the geology, we see that there is another level here with a discontinuous lines. There is a silt and clay level. This is a confining unit. It's a silt layer, which means that there is no flow that crosses this unit, but this unit is also finite. Here it has a little sand. So permeability increases from left to right. Why this? Because at the moment of the geological formation, during the sedimentation of this alluvial unit, this part here had a larger amount of clay, and this part here has a lower amount of clay and a larger fraction of sand. Finally, on top, we have another silt and sand layer that constitutes an upper unconfined aquifer. Why unconfined? Because there is no confining layer on the top. The point of showing this geological cross-section here is just to point out several aspects. First of all, the relevance of the geological knowledge to know the geometry of the reservoir that contains groundwater. The other thing is to see that within this unit, geology will be heterogeneous, meaning that we'll have aquifers, aquicludes, aquifers on the top. That's a special case. That's a real case. And every deltaic, every fluvial system may be different. Okay, so we know we need local data in order to make hydrological decisions about water resources management. Let's put some numbers on it. Of course, these numbers belong to a Mediterranean climate, and for a tropical area, they can be different, okay? But this is the mass balance of the hydrological cycle in a very small basin nearby my place, okay? The funny thing of this basin, it has an area of about 100 square kilometers. It has a rainfall of about 900 liters per square meter, that's millimeters per year, which means that every year we have more or less 100 cubic hectometers of water as a rainfall. How much water is a cubic hectometer? If you take a soccer stadium, for example, Maracanã, for Brazilians, or the Barça Stadium, okay, and you fill it with water, you may have about half a cubic hectometer. Meaning that in this area of just 100 kilometers square, every year you have a rainfall that's equivalent to 200 times the stadium of Maracanã full of water. That's a lot of water, okay? However, a 64%, if this is 100, this is 64, a 64% of this water will evapotranspirate. It will be turned into green water. We'll never see it. It's the water that all the forest, all the biosphere will use for its ecological processes. So only 35% of the water will be available as blue water. And this blue water, at 26% will be runoff, will go down, will be downstream as a stream flow, and at 10% will recharge the aquifers. You may say, okay, but we have 35%. Wait, this 25 is a water that we cannot use it in a full, because all the riparian ecosystems, all the habitats related to the stream need such runoff. So we cannot use this water. Part of it has to be left as ecological discharge, meaning the discharge that feeds the ecosystems, that feeds the habitats, and we cannot use them. Because if we use all of them, the habitats will perish, will be destroyed. And what is important from a groundwater point of view is that in a Mediterranean climate, only 10% of the recharge, only 10% of the rainfall, 110, only 10% of the rainfall recharges the aquifer. So the question is, what happens with this recharge? So I tell you, imagine a circular island, okay? So if we have rainfall, it will recharge, not this island, this one here, okay? If you have rainfall, recharge will accumulate, but water will flow to the lake or to the ocean. If we pump water from it, there is rainfall, and if we have a moderate pumping rate, some flow will recharge the lake. But if our pumping rate is very high, then the flow will be inverted and water from the lake will come into the island to satisfy our pumping rate. When we arrive to this stage, we are overexploiting the aquifer. And there is a thing, there is a risk we don't want to happen. Because this is a lake, of course, but what will happen if this was an ocean? That will mean that seawater or salt water will come into the aquifer, changing its groundwater quality and making it useless for human demand. It happens the same with rivers. Okay, before the wells, here in the left-hand side of the screen, we have a recharge. Water table moves up and down according to the mass balance, and this recharge moves to the streams. It feeds the trees, it feeds the habitats near the stream, and also some springs. What happens if we develop this area and we pump water from the aquifer? If the pumping rate is too high, we lower the water table, we consume all the water stored in the aquifer, but the worst thing is that we claim water from the river. We dry it, we kill the habitats, we dry the springs, and therefore we just do not manage water properly. In this case, we are doing a very serious ecological impact. Of course, we are doing some economical benefits here, but these benefits, these economical benefits, are not, correct if there is an ecological impact related to them. These two images explain what happens before and after water is pumped out from the aquifer. And you should have things in mind. And this is how the aquifer will behave. So what we have to do, we have to monitor the water table elevation to see if it ever reaches the bottom of the stream and dries it. This is a real case. This is an aquifer. Okay, in this well here, we have a continuous record. And you see that the water table, which is expressed here in meters above sea level from the 1970s to the early 2000, that's years, of course. Look at that. Since 1995, there is a huge decline of the water table. The water table declined more than 6 meters. Why this? Because we had a drought, no recharge occurred for 3-4 years, and the pumping rate didn't stop. So all the water resources were consumed. The aquifer was almost emptied. This is not a sustainable use of water resources. So to avoid this, we need data. We need some instruments that monitor not only one well, as many wells as possible, as many representative wells as possible, to depict the evolution of the water table. And ask managers that if they see that if they observe that the water table is declining so fast, to take prevention actions so we do not consume all the water. Because if that drought lasted for 2 years more, no water will be available not only for streams, but also for irrigation, for urban supply, for nothing. Okay? So data are paramount. We need data to know what happens, to understand how the aquifer behaves, and most importantly, to take appropriate management decisions. Therefore, that's what I said. Monitoring hydraulic head is important to describe the groundwater flow, to evaluate the amount of resources that we have in the aquifer, to know how they change, and if this change may bring any risk at all, to know whether streams will be affected by this decline of the water table, and most importantly, to promote policy actions that preserve the resource. I mean, data are not just there, I know, just to look at them, oh, they are beautiful. No, no, data are necessary to take actions to avoid risk. And groundwater, even though it happens in the subsurface, can be monitored, and we can have the necessary information to do actions that will prevent further deterioration of the groundwater resources. Sometimes the geology is more complicated. In this case, we have a large basin. There are mountains, there is a basin, there are falls, and then the groundwater flow, which is here depicted by these blue lines, can be really, really complicated. If we see it in 3D, the groundwater flow can go upward following this red line, or can go horizontally following the blue line. So the interesting point is this complexity can be known if appropriate measurements are taken. So imagine aquifers are complex things. Hydrological or groundwater flow can be complicated depending on the geological controls. However, appropriate geological knowledge and appropriate monitoring systems and monitoring procedures that will help us to know how the system works and to avoid risks. This is more or less the same example. I will not go through it. You can get these pictures later on from the references that are given in the water. Just to tell you that this groundwater flow is very slow. I mean, water in the recharge areas may have maybe decades old, or centuries, or even thousands of years old. Some water pumped out from deep aquifers may proceed from a recharge that happened thousands of years ago. That means that if water is so old, this aquifer may have a degree of vulnerability that we want to consider before exploiting it at full. However, we have several impacts on groundwater resources. Okay, and the 4 impacts I have chosen to explain briefly in this talk is a very important one from ecological purposes, which is the stream-aquifer relationship, and then other topics that has already been mentioned this afternoon or this morning, which is the overexploitation, pollution, and seawater intrusion. I mean, the stream-aquifer relationship is just to consider that there is a continuity between groundwater and stream water. You have not thought about that before, so change your mind. Groundwater and stream water are the same resource, and we can have a flux going from the aquifer to the stream. We can have a flux going from the stream to the aquifer, meaning that if a stream water is polluted, this recharge will pollute groundwater. We can have a disconnected aquifer. However, there is also a recharge from the stream to the aquifer, or if the stream is dry, there is no connection between stream water and groundwater. Therefore, the message here is that groundwater and surface water must be understood as a single resource. And this has consequences on the amount of water we exploit, on the quantity, but also in the quality. How do we know that an aquifer is overexploited? Because there is a decline of the water table. What this decline means? This decline means that the stored water in the aquifer is being reduced. In this case, we change from almost 10 meters, the aquifer, the decline of the water table was 10 meters. The problem is that the aquifer, this is the different layers of the aquifer, was only 12 meters thick. What does it mean? It means that we have a reserve that occupied a column of 12 meters of water. After this decline, only 2 meters were left, meaning that 80% of the stored groundwater resources have been already pumped out and consumed. At this point, exploitation should practically stop. Well, it should have stopped earlier to preserve groundwater storage and to preserve the communication of this groundwater with the stream and protect the habitats. However, aquifer overexploitation not only means that the water table declines, takes all of the stored resources. If we pollute an aquifer, we're also overexploiting it because we are changing its quality for bad, so we cannot use this water any longer for human supply. So if we cannot use it, it's worthless. We don't have it if it's polluted. This is another kind of overexploitation. From an ecological point of view, if the declining water table affects ecosystems as streams and wetlands, this is another kind of overexploitation. We are damaging the ecosystems, meaning that we are taking too much water than the one that we could sustainably use. And finally, another point of overexploitation, if the cost of getting this groundwater pumped out increases with time. Of course, the lower the water table, the more expensive in cost of energy will be taking this water out. So if there is an economical loss in the exploitation of groundwater resources, it also means that there is some kind of overexploitation. Pollution may come from different sources, from wastewater, from industry, from fertilization, from many sources. And pollution will, of course, make that groundwater and surface water as well, it's useless for human consumption. Not only for human consumption, I insist, but also for ecological needs. We can damage the ecosystems if water resources are polluted. And pollution, if we are pumping, pollution can be attracted to the well because pumping implies a modification of the groundwater flow. So if naturally, probably this pollution will not get into the well, when we pump, we are modifying the flow system and we can induce pollution to arrive to the well. And therefore, the water we'll get from our users will be of bad quality. And this is a thing we do not want to happen. One of the most extensive pollution sources is agricultural activity. It not only brings nutrients, nitrogen, phosphorus to groundwater, but also pathogens, antibiotics, trace metals, salt, and this everything will be, first of all, retained in the soil. And later on, with rainfall, it will leachate and recharge the aquifer. So when we pump water using wells, all these pollutants will come with water and be a hazard, be a risk for our health. The nitrogen cycle is complicated. However, in all these processes, when we put manure in the fields, all these processes end up with bringing nitrate and leaching it to groundwater. If it's true that part of this nitrate can denitrify and disappear, however, in agricultural areas, denitrification rates are so much lower than the input of nitrate, meaning that even though denitrification happens, it's not a solution and it's not a justification for adding additional nitrate to the system. Of course, taking hydrochemical data, we can know the concentration of nitrate. For example, in this case, the upper aquifer has concentration larger than 100 milligrams liters in many of the wells, being the threshold for drinkable water at 50. You see here that most of the wells, this is the number of wells, most of the wells were above this limit. However, in the bottom aquifer, most of the wells were below this limit. Why? Because the bottom aquifer is separated by a confining layer from the upper one where the infiltrations of nitrogen take place. However, some wells still show very high concentrations. How this can be? To understand this, we must know the geology, but we must also recall that when we are pumping, we are forcing a flow from the upper aquifer to the bottom one, providing that the confining layer has a small permeability. If this is the case, even though the bottom aquifer is separated from the surface where the manure is applied to fertilize the crops, okay, it may also get some nitrate, which later on will be pumped out from in our wells, okay, and therefore serving as polluted water. There are several cases, okay, some wells which are open to the upper and the lower aquifer. These ones will, of course, get more nitrate concentration, but even though we are only pumping in the bottom level, in the bottom aquifer, you may also get some nitrate because of this groundwater, this downward groundwater flux. But everything can be known if we monitor the quality of groundwater. So if we monitor the quality, we'll know the origin and the pathways that the pollution from the source to our wells, and we can act. You can take actions to prevent this. We know which pollutants happens, if these pollutants are hazardous or not to our health. Some pollutants, as nitrate, they are hazardous, but other pollutants are pesticides, they are more hazardous. So we should take care of these ones because at very low concentrations, they must be very dangerous for our health. So avoid pollution because rivers and wetlands may also suffer from groundwater pollution. Finally, I want to address the topic of seawater intrusion. Seawater intrusion, it's nothing else than the entrance of seawater inland because of difference of density. Meaning that even if you are standing here in the coast, at a certain depth, you will naturally find some salt water in the aquifer. However, if you pump, you are forcing the flow from the coast inland, and this interface, which is the separation between the fresh water and the seawater, will move towards the well and bring salt water to our freshwater resources. This is a kind of pollution somehow, because then the pumping well will provide us with a salty water that will not be useful neither for drinking nor for irrigation. Seawater intrusion has different ways depending on if this is a confined or an unconfined aquifer. It's dynamic change, but we always have this interface of seawater coming into the aquifer. I will not get into the details, but this is just to show that we can calculate the position of the interface. You will have this PowerPoint or the recording of this talk after all. And the idea of bringing these small formulas here is to insist that all hydrological processes can be calculated, can be mathematically calculated. We can use numerical models. Simple ones, like this one, it's a simple product, or a very complicated one with the partial differential equations to reproduce what happens within the aquifer. Even we don't see it, we can get data, we have models, we have tools that permit us getting a knowledge of what is going on in the subsurface, and therefore using this information to prevent disasters, to prevent risk, and reduce their occurrence, which is indeed the goal we are looking for. Seawater intrusion is all over the world, whether here in Brazil, whether in the Mediterranean. I mean, everywhere that a coastal aquifer is being pumped, there is seawater intrusion. I mean, if there is a well near the coast, there's a high probability that this well will be affected by seawater intrusion. Just to show you an example to end this lecture, this is an area nearby Girona. Of course, there's a coastal aquifer. We know the different geological formations, okay? And this is the increase of chloride in water because of seawater intrusion from 76 to 82. It went from about 100 milligrams liter, which is a concentration that makes the water salty, but still drinkable. You will not reject it for drinking. But when you reach 1400 milligrams liter of chloride, this water is useless for any use, whether domestic uses, whether irrigation, even ecological purposes. I mean, why did we have this increase of chloride? Because of pumping was so intensive that they end up bringing the interface about 2 kilometers inland, and what they get from the wells was a groundwater that in a 15-20% was just seawater that has moved from the coast 2 kilometers inland. We have techniques not only to taking samples. We can use geophysical tools to understand, for example, this blue area here means the extent of seawater intrusion. These are methods you can do geoelectrical profiles, and you get those informations. And the immediate consequence is that all the wells that fit in the blue area will have a high salinization, and their resources will be useless for human supply. Okay, I am ending this talk. I hope I have touched several aspects of interest. And my final remarks is that knowing the occurrence of groundwater resources and its dynamics, it's the way to avoid water scarcity. If we know how they evolve because we monitor and we take data, we can prevent scarcity. So monitoring and rigorous control is necessary to avoid risks. To support water resources management plans, if we do not have data, geological, hydrogeological, hydrochemical data, we cannot do any planning at all. The other point is that even though groundwater resources are in the subsurface, we don't see them. But they are vulnerable. They are vulnerable to human pressures. They may suffer from overexploitation, from pollution, from seawater, intrusion, and all these types, all these impacts, what they do is to create a risk meaning a loss of value of a resource. We'll not use salty water to cook or to wash ourselves. So I will come saying that field monitoring, research, and educating people about this vulnerability are the key to warrant a water supply of quality for any type of demand we may have. Okay, I finished the lecture here, but because this is YouTube, you may have some commercials as well. Okay, so it's time for commercial. And I thought it will be interesting to tell you, even though I'm doing the competence to the Santa Catarina State University, that at the University of Girona, we have a master's on water resources, and we have many students from Colombia, we have students from Brazil, from Ecuador, from Argentina, from Uruguay, many people taught in Spanish. So I invite you to check our website. And in case you're interested, please write me, and we'll be very, very happy to have you in this master. I mean, we benefit from becas, from grants, from the Carolina Foundation. Every year we have 2 South American students with this type of grants. So please look at the website, and if you have interest, don't call to write us, myself, or the master manager, and we'll gladly answer you. Okay, that's all. The commercials are over, only 20 seconds. That's a very short commercial. I thank you for your attention, and I thank again the Universitat of the Estado de Santa Catarina for inviting me to give this talk. Thank you very much.
Thank you very much, Pepe. When you were telling about the importance of the education, this is why we are doing this third Santa Catarina State Seminar on education in disaster risk reduction. So this is why we really understand and we really believe that the education is the way to going better and to move to a better future. And while I was here listening your words, I was thinking about the importance of knowing environments and how water is the same water as we just listened here, and how all things are connected. And this is very important because when we think about surface water or groundwater, they are the same resource. So I think this is a very important message. So we can move for the questions if our audience wants. You can ask questions. The first one is from Fabiana Moirer. Good morning, nice presentation. My question is regarding assessing groundwater usage in urban environments and how to monitor its usage at sustainable levels. Please comment on the impact of excessive water exploitation on the subsidence of lands and damage to infrastructure.
Well, thank you for the question. I mean, monitoring the use of water at sustainable levels, it depends on what you want to protect. You want to protect a wetland, if you want to protect a stream, if we want to avoid pollution, because if you pump it at a higher pumping rate, you are going to get a groundwater flow from far away, and they may bring you water of a undesired quality, of course. That depends on the goals we have, and of course on the local characteristics of the regional characteristics of the area, in this case of an urban area. About subsidence takes place when you pump water out of not exactly aquifers, but aquifers that are limited by thick aquithards, or where aquithards are important, so water comes out from these low permeability units. It cannot be replaced at all when you stop pumping, and this loss of water pressure between the aquithard produces a subsidence of the terrains, and therefore in the surface we have a small declining of the topography. This is almost an irreversible case, and of course this should be monitored not only through hydrological variables, but also using geotechnical approaches. That's not only a hydrogeological problem, but it's a geological and a geotechnical issue. When you ask about damages to infrastructures, it's more or less, it's not the same case, but it's also a geotechnical problem. I mean, when we build something upon a geological formation, of course, I mean, the pressure of this building will be shared by the geological formation, but also by the water that fills the voids within this geological formation. If we take the water out by pumping, for instance, then the pressure that was supported by the water in these voids has to be supported by the grains. And if this is an unconsolidated terrain, it will also get some kind of subsidence. I don't know now the word in English, can feel the overpressure, can, I don't know the name in English now, sorry for that. It may compress, and therefore, if the terrain compresses, the buildings you have on the top, they may have cracks, they may suffer damages, and at the end, they may fall down. That will be an extreme case. Okay, that's very common in areas that water exploitation in urban areas has been done after the buildings were constructed.
Yes, this is happening in Mexico.
Yes. California. Yes. But even here, I think in agricultural areas, where there's a lot of pumping, a few small subsidence has also been observed. However, in an agricultural area, the topography lowers a few centimeters. Well, I will not say it doesn't matter, because the surface runoff will get modified. Mm-hmm. But if this happens in an urban area with all the buildings on top, that creates a problem. But there are two different issues. One is subsidence, and the other is a compression of the terrain because of groundwater pumping in urban areas. It's a related process, but they are different processes.
Mm-hmm. Yes. Please, if someone wants to ask a question, feel free. Pep, I was thinking also about the policies. In Brazil, we have a very great difficulty in having data from surface water, and from groundwater is even more difficult. And could you please also again speak about the importance of monitoring at least the water table, because we have very, very little wells piezometers, we almost haven't. In Brazil is a very great country, and we have a very, very little network of piezometers and monitoring wells. So this is very difficult to make decisions and to think about a sustainable management of these waters. Could you please speak again?
I mean, I know I am talking for people who is convinced, but water is a scarce resource, and good quality water will even be more scarce in the future because of climate change. I know that some areas will have higher rainfall rates, others will be drier, but anyway, good quality water resources will be scarce, always, and they will be expensive. I mean expensive in the cost of having them at home. So if you want to manage them, the only way is to have data. So it's very important, and it's a very good investment, public investment, to put money into gather data. We put money into assisting people, into protecting areas, and we somehow take the occurrence of water for granted. It rains. It will rain. It would rain. Climate change will change it. Will modify this. But the problem can be the quantity and the quality. So monitoring is the only way we have to prevent hazards, to prevent a loss of stored water resources, meaning a severe affection to the quantity, and pollution. If we don't monitor things, no decisions can be made. And our politicians, people in the administration, should understand this, that investing money on gathering data, on interpreting data, hydrological data, is paramount to warrant, to ensure that people will have water resources at home, which is, I think, it's one of the human rights. It's the right to have access to good quality water resources. So how does monitoring proceed? Which kind of monitoring do we need? This is a question that has been addressed by the European Water Framework Directive. It will take the whole afternoon, the whole evening to explain, to deal the topic of how, where, how often we should monitor an aquifer or a stream. So I invite you to go to the European Water Framework Directive website and check all the documentation related to monitoring procedures. They are very useful, and that will tell you how to start monitoring a given aquifer. I think we have any monitoring well. Where and how often do we conduct a monitoring method or procedure or whatever you want? Okay? So we'll go to the European Water Framework Directive website. You will find, maybe at the United States Geological Survey too, but because in Europe we started more or less not for nothing, but we started a few years ago, 20 years ago, to put things in common, then all these manuals are really useful. They're having useful, for instance, countries like the ones from Eastern Europe that have joined the Union very recently. They had the same situation as you had in Brazil. Very few monitoring points. And because the Union is asking them, if you want to become European member, then you have to follow the European directive, these manuals tells them how to do things in countries that will be more or less in the same environmental, let's say, lack of information that you described for Brazil. So I address you to this website, the Water Framework Directive, and look at there's a lot of information, but you look for monitoring procedures and you will get a lot of details.
Mm-hmm. Yes, yes. This is very important. And we need also to convince our politicians, because things needs to go in a more sustainable way, because until now we are still waiting for I don't know what. So this is a very important issue to be discussed and to change in Brazil. Let's see if you have other questions here. Just a minute. If someone are asking questions. Let me see. Is there any standard way to calculate such contribution of different? I cannot read here. Different variables in mass balance for other regions. Maybe I cannot read here. Veraldo, could you please check?
I cannot see it in the chat.
Yes.
Yeah,
No,
I will
because...
just add on the chat here.
Okay.
And
Because
maybe Lakshmi Tapa can help too.
we remember you saying that evapotranspiration has 60% of its contribution in Mediterranean for mass balance. How is this percentage contribution of evapotranspiration is calculated in mass balance?
Well, evapotranspiration is a tough variable to calculate. You cannot measure it. Well, you can at a local level, but you cannot measure it at a regional level in a whole watershed. So you have to use empiric formulas that uses variables as temperature, mainly temperature, air humidity, wind speed, irradiation, solar irradiation, and these formulas using this data, which are measured at the weathering stations, then you calculate the amount of evapotranspiration. This is the way that that this number of 60% was calculated. Okay, it's just using formulas.
Mm-hmm. Hot reefs, that formulas, huh?
They're not. There are many formulas. It depends on your case. It depends on the variables you have. For example, if you only have temperature, you are restricted to use Thornweight formula. It's a formula by a Swedish guy called Thornweight. Mm-hmm. That has been working since the 50s. Mm-hmm. Or if you have more data, you have the Penman-Monti formula, you have the Bradley formula, you have several other ones that give you a better approximation to your case. But go ahead, Virginia.
Lakshmi? We are not hearing you.
Me?
No, Lakshmi. Can you But we are not listening you. Try now, please. I'm not hearing. Do you, Pep?
No, me neither.
Mm-mm. Question.
I believe there is something on her microphone.
Yes, just a minute. I will see the chat in YouTube.
We answered this question before.
Is about, I think, agricultural activities. Is this Lakshmi? Yes. Yes. Agricultural activities are one of the major contributors of aquifer exploitation, but we are directly dependent on agriculture for food sustainability. So what could be possible ways, activities to, I think we, first of all, we need to change our process in agriculture. I think this is one of the ways we can make this change. But what do you want? What do you think, Pep?
Yeah, that's a difficult problem because we need food and we need water to create food. But if we overexploit the aquifers, we are running out of water. So at the moment we do not have water, we will not be able to grow any vegetables. And the way is to reach a sustainable level. For a given region, I can use this amount of water every year for irrigation. If you take more because it's a dry year, well, you better wait that the next year is a wet one, so you recover your water reserves. If you are in a drought and you are insistently pumping out from the aquifer more water than it's recharged, you are doing water mining. And water mining means that you are turning water to a non-renewable resource. And it will happen that, I don't know, in the near future, you will run out of water. So you will not be able to grow food anymore. And what I'm saying is very obvious. So what is the point? The point is that you should monitor the water level, the water quality, see the evolution of the water table in this aquifer, use models to contrast recharge with irrigation uses, irrigation demand, and apply some policy restrictions. A paradigmatic case is what the people in the Sahara is doing. They know they have hundreds of meters below the surface, they have aquifers that were recharged thousands of years ago, and that today there is no recharge at all. But they have a huge volume of water stored underground. So they decided to use this water to irrigate and produce food in a desertic environment. But they know that they will be able to do that for a given number of years, for 20, 30, 40, 100 years. But they are mining that resource. And mining means that it's a non-renewable resource. So it will come a moment when there will be no more water for these crops, which will have to be abandoned. But meanwhile, they have been profiting from these water resources, what they are called fossil water resources, to get a benefit, to produce food. What will happen next? You need an alternative. I mean, but if you have groundwater overexploitation because of agriculture, that means that you don't have a water resources policy. you don't have a management plan. And if you have one that allows overexploitation, it's a bad management plan. I know that some wells are illegal, that there is no policy control. But anyway, these facts do not solve the point that if there is aquifer overexploitation, this is a very, very bad scenario.
Yes, this is a real paradox, because it's a problem without a solution. Yeah.
Well, the solution is getting aware about groundwater resources, about how they work, what is their natural dynamics, and how far can we exploit them.
Yes.
It's recognizing that we as human beings, we can or destroy or save the planet. This is the topic, of course. But policies are for this. We have to take care of our garden.
Yes. Here we have some thanks for sharing this knowledge. We appreciate it.
Pleasure.
And let me see if you have other questions. I don't think so. Veraldo, do you see questions or not?
Yes, there is one. I will highlight it here.
What is your opinion on recharging aquifers with treated sewage effluents in some coastal areas?
My opinion is that it should be, there is no sense of dumping treated sewage effluents to the ocean. Bring them back to the stream or recharge the aquifer with that water. Nowadays in Barcelona, in the Catalonia region, we have a very severe drought. The city of Barcelona, about 3 million people, has no water shortages still, because they are recharging treated sewage water and they are using a desalination plant at full. But recharging water should be mandatory in all coastal areas. There is no meaning. It's stupid to get the volume of water, even though has been used, to dump it to the ocean. Bring it back to inland and use it again. Of course, taking care of the quality. Nature, if it infiltrates, nature will somehow degrade some pollutants. Others maybe not. But the recharging actions must be followed by a strict control of the quality. But recharging is being conducted in many countries, and it's probably a very efficient way to restore water back into the natural system for later use for human supply or by environmental purposes, I don't know. But what we cannot do is just put this water to the sea. We have to take it back inland and bring it back to the hydrological cycle. Indeed, I actually support all these recharging operations. Of course, with a good quality control. Okay, yes. Good question. Good question, because this is something that water supply companies and water treating companies should start asking themselves, what do I do with the sewage effluents? Reuse again. They have a value.
Yes. Yes, this is true, because our water is finishing. So our clean water, our blue water And so we need to change our point of view and reuse waters. This is what we need to do.
Certainly.
Yes.
Certainly.
Veraldo, do we have questions or it's enough?
No, I think it's all.
So we have done for today.
You can actually close the webinar.
Okay. So, Pep, it was a very great moment to sharing knowledge and to discuss about important issues on water resource management and disaster risk reduction. And we thank you very much. We thank you for the beautiful speaking the presentation, and also to attending our invitation again. So
thank you for the invitation.
Veraldo, if you want to say some words. I don't know if now Lakshmi can talk. I don't know. Not.
I think she has still an issue with her microphone.
Yeah.
Now,
yes.
Can you hear me now?
Oh, yeah.
Oh, yes, we can.
Okay, sorry. I was not aware what the issue was, but like Virginia said, it was really nice to have lecture, like a presentation about groundwater and like importance of groundwater. And I think the lecture was really nice in terms of theoretical foundation, and also to know about different aspects of groundwater. So I would also like to thank Professor Josep for this. And also at the same time, I'd like to mention to our attendees that we'll be having series of virtual webinars, tutorials, and lecture series like this in our future. We'll try to put all this information in our social media too, and please keep your eyes on our social media posts too. With that, yes, I'd like to thank all the participants again, speaker again. That's all from my side. Thank you.
Thank you.
Okay, and just again, thank you a lot, Joseph, for being here and attending our event. It was the first talk on our
so
series.
Important, Pep.
Yeah.
I'm sorry, I thought it will be shorter. Anyway.
No, it was perfect.
And yeah, it's just we hope to welcome you in Brazil in near future, so you that can be here as well with Laxma too.
Yes, we are going to make some meetings in Brazil, Veraldo. Actually, we just had a positive result in a project we sent last year. And so Pep is coming to Brazil.
Hope so.
Nice. So I just want to acknowledge again to Virginia and Laxma for being the shares for today. And again, our lecturer, Professor Joseph Maspla, for delivering actually this nice talk and bringing some new insights for our students. So again, thank you again.
Thank you.
You're welcome. You're welcome. Thank you.
Bye, guys.
And now we close.
Ciao.
Bye-bye.
Bye.